Okay. Yes, question.
Can grade go up to 50 or above?
Okay, so up to 50 because you're just making the corrections. The people who typically didn't do the ALU was worth 10 points. So the people who didn't do the ALU, they can only, there's 5 points that you can't get no matter what. Those people who did complete the ALU, you can earn up to the remainder of what you had. So that's the way to reward the people who got the ALU done. So on the projects, in a typical undergrad project, the grade distribution will go something like this. Okay? So you have 3 or 4 groups that'll have like 48, 47.5, 47. Very few, like nobody got like no group's got like a 43. And then you get down to 40, 39, 37 here. Okay? So I want to talk to you guys about the importance of planning your projects out. I was not surprised by any group's grade. The groups that did very well, got these kinds of scores, were the ones who were emailing me during the 3-week period asking, hey, here's a question I have on this, here's a question I have on this. The groups that didn't, not coincidentally, were down here. So this means that the groups that are down here are procrastinating. Giving you, now, one first thing I want to talk about is the proper way to ask for an extension. So I extended the first assignment, right? And the reason why is a couple of people in a group came to me and said, hey, we're rushing a fraternity and we have this set of issues. And normally I'd be like, well, you got to learn how to balance your time. But the thing that that group had done is they were actually actively doing work. They were showing me they had a set of work that they were doing, and then something came up. That was the first weekend where they had to go to all the events all day long, and if you missed them, you had to pay $1 billion to Bill Gates and sacrifice your firstborn or something like that, right? But they were actively doing work. They showed me they made an attempt to get the work done, and then something came up that made it impossible. And I went, okay. Sure, in that case, absolutely. They've demonstrated that they've earned the extension through work and product. If you come to me with like 30 minutes left to go or 5 minutes left to go and I've never heard from you and ask for an extension, and there's like 3 or 4 people laughing because you know who you are, you're not going to get one. Yeah. but there's a right way to do it and a wrong way to do it. And the reason I mention this is I was actually talking to a captain who works out in Sandia Labs, and at one point I was like, oh yeah, I just did this group project, and I kind of casually mentioned, oh yeah, one of them, not one of them, like there were 3 groups who asked for an extension in the last half hour, and he went on a tirade. He was like, you know what, that would tick me off. I did that, fire him, and I was like, all right, sir, that's not why I called. I'm calling about grant money because I'm a tenure track professor, and that's what I'm here for. But the reason I'm saying this is because you never know what kind of person you're going to run into when you get out to industry. You might run into the type of person who will work with you. You might run into the type of person who doesn't like people. That happens. How many of you have met an engineer who doesn't like people? That should be everybody, right? Sheldon? Yeah. We all know Sheldons, right? And so you have to learn the proper way in which to convey. I'm pretty laid back about certain things, but I want to make sure that all of you succeed. That's my goal. But at some point, if you're the type of groups that are over here, and you want to be over here, there are certain ways to do that, and it's better time management. Now, there is a method to my madness. If you look at my lectures and you see, let me scroll down a little further, and then I have the VHDL assignments posted on Blackboard, but I also post them in the middle of the notes, right? I'm posting them here because at this point, you now have the knowledge to complete the problems. Now, the reason why I'm not making them like weekly assignments, like I initially thought, is because you guys have lives, you guys have other courses. I don't want it to seem like the only thing in your life is ELE 385. It's actually kind of a pathetic life, right? But there are people who will see this, and then we'll work on it a little bit, struggle, and then they'll ask me a question, I'll answer their question. And then instead of, on the last day, furiously trying to get it all done, they are putting the pieces together. And that's how you gotta, work when you get out into industry, or if you're the type of person who's sadistic like me, you want to go to grad school. That means there are deadlines, and eventually, if you're the type of person who can't meet deadlines, you're the type of person who doesn't have a job. And so that's how I encourage you. There's still 2 more regular assignments, and then the final project. So there's a lot of grade to make up, meaning that you're not stuck in a hole. If you got these kind of B's or C's on the first project, it doesn't mean you're hopelessly stupid. I've not judged you. And ideally, I would love these grades to be up here. Not only does that mean I've developed more people, but these are easier to grade. These are a lot easier to grade. Oh, that's right. Oh, that's right. Check mark, check mark, check mark, check mark. These are the ones that'll take me a long time, because then I have to make comments as to why it's wrong and what you did and what you need to improve. It's mutually beneficial. And also, you want to have your code development, so that way when you're applying for jobs, like, hey, look what I did. That's the whole goal. You should have this set of code that makes you stick out to other people. So in this section, your next assignment, we're going to be covering a lot of finite state machines. So up to now, you've done combinational logic, input in, input out. So now we're going to deal with memory elements, saving information in order to contribute to the next state operation. If you recall, very briefly, we discussed the concept of Mealy and Moore machines. We also discussed them last class. Topical guide objectives 1 through 3.1.12 was where we did the background. And example 1.1 and 1.2, which you've already covered on the exam, but that's how, if you're trying to bring yourself back up to speed, that's what you need to review. And then the sequential logic, you have input states, you have the function, and your output state is the result of the current state you're at plus the input. And then we've defined Mealy and Moore machines in different manner, where the Moore machine is a combination of, the output is based on your current state, and the Mealy machine is a combination of your current state and the input. So in a sort of an interesting development, something happened this morning that will tie into why I'm telling you very much about make sure you get to undefined states and make sure error checking and timing is important. And here's a case of what happens when you screw that up in the real world. So I went over to the student union, and I want to get Coke Zero. That's my beverage of choice. And I put in a quarter, and then I put in $1, right? So it initially rejects the $1 because it's kind of crumpled. I'm like, oh, crap. So, all right, now put the $1 back in. It accepts the $1. I press the button, and it bends me it bends me the Coke, but then it rejects the $1 again. So if you can see right here, it's bending, but it has shot my $1 back out. This really happened this morning.
Which one was that?
The one at the student union. So this was at 7:30. So at this morning, so I found the Coke vendor was actually there. So the reason I have a photo of this is because we were able to replicate the area. We took another $1, crumpled it up, put it back in, put it the exact same way, and it happened. So why do you think this occurred? So the guy went in, and you're not going to be able to find it because he went in, he reset the machine, turns back on, the error doesn't happen anymore.
You got 2 free Coke Zeros.
No, I gave him the money.
Oh.
I'm an engineer at professional applications, and integrity is doing the right thing when you think no one is looking. Here's a recording. Okay, so, but yeah, so that's but these things are what are known as embedded systems, and let's going on is you're loading it up, and you have a set of states. You have an initial state reset state, right? Where let's do you have an initial state like we talked about last class, and then you can take in nickels, dimes, quarters, half dollars, and full dollar bills, right? So what's supposed to happen is that let's say we had this issue at 0 cents, and this particular case I put in a quarter, and it gave me to this state where that's 25 cents. Now, there's another state where I put in a dollar. If you put in the dollar, it gets to the 125, which is then supposed to allow you to bend, correct? But let's say this is a dollar, but at each state there should be, if the dollar is bad, it should then reject the dollar and outputs it back to the user, and then brings you back to this state to indicate that you still only have 25 cents, right? So then, what ended up happening is that, okay, it accepted the dollar initially, but there was still information that it said it was still here, right? So as a result, it vended me the machine, but then rejected the dollar, and as you saw, I mean, you probably can't see this, it still indicates that there's 25 cents. So it's vended me the dollar, it has returned the dollar to me, I have the Coke, and there's 25 cents. So I could actually push that button and get the refund on the 25 cents. So if Coke didn't luck out and have an electrical engineering professor come by instead of, sophomore student who saw this, like, oh my gosh, I can't believe what happened. And what happens is they lose thousands and thousands of dollars today, right? And guess who's in trouble? The person who who wrote the program, right? And guess who writes the program? Electrical engineers. That's you guys, right? In the future, exactly. So this is why. And I'm not making this up. This did happen this morning, and I was able to take the photo because we replicated the error. And next year I have to say, well, last year. But this is an example of what happens when you don't take timing into account, when you don't do undefined states and all of that. So, yes, Adam.
Why would resetting it fix it if it's in the program?
Because if it's an issue. As you guys have found out dealing with Xilinx, loading the program can sometimes be a pain in the butt, right? So what happens is you can get bugs based on if it's they have resetting it implies that they have a program stored and then you load it into an embedded system. Like you guys are going to be working on loading things from the computer onto a board, right? So what happened is the Coke vendor had a base program in his computer and then loaded it on that one. So they reset it. That's fine. They didn't just press a button and reset it. He actually loaded the base program, which is the way it should have been. So whatever program they had loaded up, whatever the last vendor had an issue. That's a good question. Any other questions about this?
So what happened was that it.
When it didn't properly, like we discussed last class about if-else statements, we have these if-else statements pertaining to states. You're supposed to go to the state, and then the information is supposed to be just gone.
Yeah.
But sometimes you have these global variables that you're running, especially if you code it in C or C++, like we were talking about earlier. Oh, you remind me before we leave class that I need to talk about this coding thing. And by going here, it's supposed to update the global variable. And my guess would be that it didn't do that. So there's probably some variable called reject $valid equals 0 or something like that, some semaphore or some binary value. And it's supposed to be, it was supposed to be set back to 0 because the dollar is no longer in the system, right? But didn't get updated, so therefore it got here, and then simultaneously ran the vend program as well as the reject the money program.
So the timing issue or memory issue?
This would be more than likely a timing issue. Because it's supposed to reject it and then on the clock go to the next state. This is why we're going to be doing a lot of edge triggered memory operations. Because if you do level sensitive, and you get multiple inputs on the level, then the output will change multiple times. Whereas if you do it on the edge, then it can only change as the transition occurs. And that's it, it will hold it. And we'll see examples here in simulation of how it works. So I don't know, I didn't dig around into the code, I just wanted to, it's an amusing coincidence. Oh, I'm teaching finite state machines today in class, this is cool. And the code vendor guy did not think so. But anyway, so here's a simple Moore machine. And as we discussed this one already in class, with A, B, C transitions. Now the key thing is comparing this to the actual implementation of VHDL. So you have remember if you recall from last class, we had a new type called state types, right? So I have A, B, and C, as well as this undefined state U. So the reason why my first case is if reset is equal to 0 is because I want to be able to get to the initial state. We go back to our Coke machine, FSM. Every time I bend, right, I should be able to have the next person who comes by be able to buy a soda, correct? If you don't reset the FSM, then it's just only one person gets to buy a soda ever. And person number 2 is not happy about that. So we have to reset it. Additionally, if you get if you get some sort of error on undefined input, you don't want to just be permanently broken. You want to get to the point where you can try to start it all over again. So when we get to the data path, those are known as exceptions. In this case, we're just going to use a reset signal to completely reset the finite state machine. And then we have what happens if it's A. If it's 0, it's going to stay there. If it's 1, it goes to B. And else, it's going to go to U. And then if it's B, it goes back to A. If it's 1, it goes to state C. If we don't have anything else, we want it to go to the undefined state. If it's C, if it's 0, it's going to go to A. If it's 1, it stays at C. There's no case where it goes back to B. And then else, it's going to go to U. And then end if. And if it's case U, it's just going to stay there until we get the reset signal. And then the second process, we're now allowed to have 2 processes in here for sequential elements. So what happens? If it's Y, if it's in state A, we're just going to output as 0. So this is where it becomes uniquely a Moore machine. If it's B, Z is going to be 0. If it's C, Z is going to be 1. Just like we indicated, Z is 1, Z is 0, Z is 0. And then end case, end process. And I've done a test bench here. We initialize everything, reset as 0, signal W, and then we have your outputs, clock signal. If you recall, I demonstrated last class, if you have some sort of input port clock or CLK, remember how before it's going to generate these brackets around the clock and you had to get rid of it, it's a small pain. But now you actually have a clock signal. So it will actually properly generate it to match precisely what you have as your inputs. If we had CLK here, this clock generation process would be CLK, 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 and so on. So it sets the time period, and then every half of the time period is positive, half the time period is negative. And then I initially set it as 0, and then the first thing I do is make sure to set reset n equal to 1. This means that it allows proper operation. A common mistake I've seen in the past is people are testing and they can't get the FSM to work to save their life. Well, it's because they didn't set reset n to 1 in order to let the thing properly operate. It was just going back to set to stage A. And so based on this particular simulation, this is what we got in the output. You see the undefined values, and I have a propagation of 10 nanoseconds, which is what we expect. really hope you guys can hear my voice and not the construction going outside on the video. So for the Mealy machine, it's a little different. You have A's, if it's state A, if it's 0, you're just going to output a 1. If it's going to be 1, it's going to output a 0. So the transitions correspond to the outputs. So in this case, we have, I think, section 4 Mealy machine. We had two states, A and B, so I've done A, B, and undefined. Process, reset, and clock. If it's 0, it's just going to stay at A. If we set it to 1, then we can go to our A value, where we are this process block defines the transitions between the states, and this process block defines what happens once we've accomplished the transition. So if A is, when we get to state A, if we leave state A and we do W, then Z is going to be 1, then else it's going to be 0. So this is how we differentiate it and make it to a Mealy machine. Here I have Z is equal to W and B. And the reason why I've done this, if you look at transition 0 is going to be a 0, and transition 1 is going to be a 1. So that's an opportunity right there to reduce the amount of coding, that 1 or 2 lines, but that's it's a small reduction in amount of code. And when it's U, I want to stay in U until we get our reset signal. And then again, I've included the test bench here, generate the clock pulse, clock period, and then here you can see what happens when it's W, it's 1. Now, why do you think this kind of has this short, this is kind of a reset thing. Why do you think that it is here, but then switches back here kind of quick? What do you think is going on? I'll scroll it up so you guys can see. This is a properly operating FSM, by the way. Why do you think this is occurring? It hits here, we hit our clock period, and it really only seems to be happening at these changes, right?
Make sure it's correct. It's not rejected, like the dollar.
Right, well that's what happens over here. I'm talking about this here. So you have this transition here, and then we get to a 1, and we've gone to our next. So it doesn't really change until this negative edge trigger, which we have, and then we get to this next negative edge trigger, and look, it's changed again. So when it's 1, and we got our trigger, and reset is 1, this is actually a case where it's changing states. So it's going to be 1 and 0, but it's staying at 1 here. That's because if we look at our finite state machine, we're getting to this point where it's just staying in state B. So it's proper operation. So knowing how the FSM works and comparing it to your simulation is important. So I mentioned last class, there's 3 unique course objectives that you'll be meeting in this particular section. So describe the differences. We're going to talk about latches and flip-flops. A latch, as I mentioned last class, is asynchronous. It's level sensitive. And level sensitive means it can change at any time while it's the level we're expecting. So it's a level sensitive SR flip-flop for a positive level sensor. That means any time, at any point during the clock period when it's high, it can change. So if you get a switch and then it changes again, that's what occurs there. Flip-flops occur that are edge sensitive, meaning that it has to wait until you actually get an edge change. So it can only occur here. So in this case, if we look at this previous, I'm going to scroll back up for a second here. You see how it's only occurring when it corresponds to the delay after the edges? That's because we have coded it clock event and clock is 0. This means it is edge sensitive and occurs at negative edge triggered.
So if it was level, then what was the state?
Oh, if it was a level, then you just get rid of clock event. It would just be else if clock is equal to 0, meaning that any time in your transition 0 and 1, if it just said that, from here to here, any change could occur. By limiting it to the clock event, it only can occur here. So that way you can regulate timing better. So, and then I've showed positive edge and negative edge. I've showed the example of the code here. And so the fundamental latch is known as a set reset latch. In each of these topical latches, I've included the finite state machine, the truth table, and the implementation at the gate level. So here, when it's A, it's just going to, I call state A is when it happens we have 0, 1, and B is state 1, 0. So when it's 0, it actually should just go back to its original value. So when set is 1 and reset is equal to 0, then I want to have Q is 1 and Q naught is equal to 0. And 0, 1 is the reset to set Q is equal to 0 and Q bar is equal to 1. Now, if you recall last class, I showed you this simulation of, let me just go down here. I showed you this simulation, right? And that was based off of a VHDL. So this is topical got objective 4.5. So when set and reset are both 0, it should stay the same. When set is 0 and reset is 1, you should set Q equal to 0 and Q bar equal to 1. Set is 1, reset is 0, set Q equal to 1, Q bar equal to 0. Now 1 and 1 is this undefined state, and that's what we're going to talk about next. Here's why this is important. Because in this VHDL code, I don't have timing. I've used the 2 NOR gates just like we've done up here. And if you recall, when we had 1 and 1, it's just going to toggle back and forth because the timing's difficult to maintain. So I've created 2 wires, I have 2 NOR gates, and then I've mapped SR to Q and Q bar to the outputs. And so I've done the unit under test here, and then I have 1, 0, 0, 1, 0, 0, 0, 1, 1, 1, and so forth, just to show the point. So here's what happens. When it's 0, you're going to get this toggling back and forth. And you get 0, 1, and they map correctly as we expect, right? And then you get this 0, 0 again, and you get this weird toggling all over again, right? And we showed you why, because what happens here is you get 0 and 0, and it's going to match. If it goes here, you get a NOR, you're going to get a 1. And same thing, you're going to have a 0, you're going to get a NOR, you're going to get a 1. So you get 1, 1, and that's going to put them back here, at which point, by putting a 1 on there, you're going to get a 0, 0, 0, and that's how you get the toggling, because it's going to keep toggling. So how do we create SR latches and prevent this problem from occurring? Use the case statements. So there's pros and cons to this approach. The con is that you gain a little more area, but the pro is you're able to maintain the integrity of the finite state machine. Now, if you're designing this in CMOS, so those of you who are interested in taking my class next semester, you're going to actually need to design SR flip-flops in the manner I just showed. You're going to have that toggling issue. So how do you think you could potentially stop it? What do you think you have to control? Yes?
There's some delays.
I'm sorry?
Very delays. Delays.
Delays, exactly right. You have to ensure that you have to kind of drag out your clock signal and make sure it's edge sensitive. And this is where edge sensitivity becomes important, because if you get this issue where you're going to get Q and Q bar are going to come out at different times, if it occurs before the edge, then that's okay, because once it gets to the edge, they'll both be the correct value, and that's what truly matters. Sometimes we were inserting, and that's why I've been so insistent on you ensuring that you do proper buffering and ensure timing, because I want you guys to understand this concept here. Because if you don't do that, then your Coke machine is giving money back to the Ole Miss students. And while Coke does certain charities, we are not one of them. So case A, if its state is 0, it should stay there. If S is equal to 1 and R is equal to 0, then it goes to B. And then I've set else's to define. So that could count as 1 and 1, or if you get undefined values, because we don't want to get to that other state. Likewise, if we're in state B, if reset is equal to 0, then we're going to stay there. If it's set is equal to 0 and reset is equal to 1, that means we want to set Q to equal to 0. So as we go back to state A. Otherwise, we have an undefined state. And then here, process, when it's A, this is Q is equal to 0 and NQ is equal to 1. When B, Q is equal to 1 and NQ is equal to 0, and it's undefined, they're both going to be undefined. Now, this is an important point in any latch or any flip-flop from here on out. I want to emphasize this point. Very important in testing. Very important. Very important. If you turn in an assignment that doesn't do this, we will have problems. You will lose much points because it doesn't work. Q and Q not and not Q. What does not Q imply? What's that? The inverse. Yep. So if it's not Q, that means it's not supposed to be Q, right? Q should never equal Q naught, ever, in any of your designs. If it does, it means it doesn't work, and you don't have a flip-flop, you have garbage. When I was in, I won't go into as much detail of the story in class, but when I was in nuclear power school, we were learning about JK flip-flops, which you're about to learn about here in a minute. And our senior chief who was teaching the course was going through the same concept, and he sounds a lot like Marvin the Martian, senior chief Bennett, great guy. But he goes in, he just jumps up on this table right in front of us, and just jumps up and goes, and he sounds like Marvin the Martian, just hilarious. And he's like, Q never, ever, 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 effing ever equals Q naught. Never equals Q naught, okay? Are we all on the same page? So that's how they pay attention. Jump up and down like Marvin the Martian. Got it. That'll come back on the teacher evaluation. And so here's the proper simulation of a SR latch in this case. So the SR flip-flop is how we do the same thing, except when we set it equal to when the input for the clock or enable. So in this case here, enable is equal to E, or you can tie it, a lot of people will tie it to the clock. When enable is equal to 0, I don't care what's going on, it should stay in the same state, right? So when enable is 1, it should just have the exact same operation as before. So enable is equal to 1, then we have 1 and 0, then your set is equal to 0, and your reset is equal to 1, and then it works just normally. And this is the logic symbol you'll often see. I've made sure to just include it for your edification. Set, reset, clock. In many cases, you'll see a kind of a small triangle here. Sometimes you won't. I'm trying to remember which guy it was. It was a different guy who was interviewing. They were interviewing at AMD, and they were very adamant on people including clock signals in their diagrams because they'll have you go up in a giant whiteboard and you have like 4 or 5 people asking you questions. And Sumirup was saying how, if he had forgot to draw a clock in any flip-flop anywhere like they were supposed to, they gave him a lot of grief. So in any of your diagrams or any of your drawings, be very clear to include the clock signals where they're supposed to be. And so here is kind of the SR flip-flop code for in VHDL. So I've done the clock event, and clock is equal to 1, so this makes it positive edge. Now if you notice, I'm kind of going to show you guys design methodologies. I have this only thing that says only the only different line, right? Everything else in here is the same. So you could even put if clock event and clock is 1 and then just have them map to an SR latch, right? You do that. You can, here I've just copied and pasted. If you go up here, lo and behold, it's the exact same code. So this, what you should be doing is you're seeing opportunities for code reuse with your own code. And here the process matches exactly the same. So it's the exact same file. I've changed one line of code. And then I've included a test bench. The test bench is also identical. And then here's the simulation. The clock pulse, you see it's going like this, going like 0, 0. It's not toggling like it was happening before. And then reset becomes 1. Well, we're already at the stage where it was initially 0 and 1 before, so we're there. We switch to 1 and 0, and after a delay, it changes. And then no matter what pulses, as long as it stays the same, it's not allowed to change at all. And then the moment it changes again, it changes immediately on the clock pulse. And we're getting undefined values here on the inputs. So the reason why is because we're getting 1 and 1 on the SR latch, right? I'm sorry, let me scroll up. So we're getting 1 and 1 here, right? We're not supposed to get 1 and 1 on an SR latch input, correct? So now we have undefined values. So, but there's ways to improve this. How can we manage the latches and the flip-flops to ensure proper operation? Well, the D latch just basically takes the concept of the SR latch. So you have this SR latch here, right? And just says, well, if problems occur when SR is the same as R, well, what happens if I just take D and invert D input? And so S and R to the SR latch will never be the same. That's what the D latch is. So the truth table now is significantly reduced. If it's 0, you have 0 and 1, and Q is 0 and 1. And if it's 1, you have 1 and 0, and Q is 1, and Q bar is equal to 0. So state remains the same, and then reset. So before I show you the VHDL code, what do you think would be an idea that you guys could have to reduce the amount of work you would have to do a D latch code? Bear in mind, we've already showed you the SR latch and SR flip-flop. Instead of writing out the finite state machine for this, what do you think?
Just call in the finite state machine and an inverter.
Have an inverter and finite state machine for the SR latch, right? Bingo. That's exactly how it's done. So instead of writing all this new code, you just have an inverter, invert not D, and then you map it to an SR latch, FSM. And there you go. Miracle. Magic. And so make sure you guys can see 4.7. And so 4.8 is the D flip-flop. So you have the same edge. You have an SR flip-flop. And D, you've just inverted D and S. Same truth table. When the clock is 0, it should stay the same. When clock is 1, D is 0. I have these little SNR equivalents to show you how it's propagating through the, I'm sorry, let me scroll up so you guys can see. So I have this SNR to show you where you should be and how it's propagating through, and then Q and Q bar. And then here's the logic symbol. So this triangle here is often represented as clock. So at this point, you now have the knowledge to do the first 4 VHDL problems. Finite statement, and here I've indicated differently. If I say you're using an FSM, you're allowed to use those if-else statements because that'll ensure proper timing. Design and test a structural architecture, the SR latch, SR flip-flop, D latch, and hopefully you guys at this point should see the pattern be able to do the D flip-flop.
Is this lecture 11?
Yes. Okay, so let's cover the concept of master-slave flip-flops. So I kind of I've alluded to this little spiel here about in each of these latches and flip-flops, the state of the gate keeps changing according to the values of the input signals. So it can change multiple times when the clock signal is active. So that means it's level sensitive. So if it's edge sensitive, you can stop it from toggling. And there's a need for storage elements that can change their states no more than once per clock cycle. So now we've eliminated that issue through edge sensitive coding. So here we have this concept of a master-slave flip-flop, and these are actually very useful in design. So you have two D flip-flops in series, and you have a D input and a clock input. And then here's what happens. It's going to invert the signal from the clock, which goes to the clock of the second flip-flop, which we call the slave flip-flop. And so the idea is that instead of having the input from D propagate to the slave, the Q is going to drive the D on the second flip-flop. So the master one, the slave cannot toggle, this cannot change its state until the master does. So that's why it's called master-slave. So the idea is you get a 1, it puts a 1 here. So if it was a D, it was 0 here, then it becomes a 1, and then we'll do so. So then the reason why we invert the clock signal is so that if it waits until this is done, and then flips to 0, so it's the second half of the clock pulse, correct? Then it can change, and the results are propagated to the output. And so this example question is a good description of how master-slave flip-flop works. So given the following time diagram for clock and D inputs, draw the appropriate response to the QM signal and the Q output for a master-slave D flip-flop. So this QM is Q middle, and Q is Q output. So here's what happens. We get time 0, and clock is equal to 0. We've changed clock is equal to 1, and then here's what happens. D changes, and then that immediately changes Q. And then here's what happens. So 0, once that changes, then it propagates. Oh, I had it backwards. I'm sorry. Q is this one, and QM is the output. My apologies. So it doesn't stand for QM middle at all. Okay, so here's what's going on. Clock 0, clock becomes 1. Once the D changes, then the first clock Q changes as well. And then, because we have inverted the clock pulse, this isn't going to be 1 until clock is 0. So once clock is 0, it's going to affect the second flip-flop. So now once clock becomes 0, then the QM output is driven by this signal, not this signal at all. So it becomes 1 when this value is 1. So then we're going to propagate along, nothing changes. Then we have a positive edge. Well, now this is 0, right? So now the in-between Q value changes to 0. And then it waits until we have our negative edge, at which point that's when our QM output changes to 0 as well. And this continues to change. So when it changes to 1, D happens to be 1, so that's when it changes here. And when it's 0, QM becomes still 1. I'm sorry, when it changes to 0, Q is now 1, so therefore QM becomes 1, and so forth. Does that make sense to everybody? Okay. So I have written the code for a master-slave flip-flop here. So I have D flip-flop component. I have an inverter wire and a signal QM. And so I've the master and the slave. I've hooked up the inverter to not clock. D's flip-flop is also port mapped to the connecting wire. And you have the wire, and then you map Q and Q not to this Q and Q naught here for the master slave flip-flop output. And then this is the simulation based on so whenever Q becomes 1, so you have D, and you notice how it'll change and it'll wait until the next clock pulse, and then it propagates after the delay. So the reason why it also doesn't match is because the D flip-flop has a delay of 10 nanoseconds, right? So then you have the 10 nanosecond delay, and as you can see, it maps as we expect. So 10 nanosecond delay, and then it becomes actually 20 nanoseconds because we have 2 D flip-flops in series that it's going through. Does anybody have any questions on anything I've covered so far? I think my impression is a lot of this is review. Okay. So then here we can start combining some concepts. This is an example here. Design a D flip-flop with preset and clear signals. So the idea is, hopefully you guys can see that. If clear is equal to 0, then we want Q equals 0 on the output. If preset is equal to 0, then we want Q is equal to 1. And if both are equal to 1, then we want normal D operation. So these are negative level censored clear and preset signals. So here's what's going on. We draw out the truth table. When it edges 0, we just want it to stay in the current state, right? Just like before. When it's 1, when clear is equal to 0 and preset is equal to 0, we don't want anything to happen. When it's equal to 1, here, when clear is equal to 0 and preset is equal to 0, that means we want 0 driving it, and we want Q is equal to 0 and Q bar equal to 1. When clear is 1 and preset is equal to 0, that means we want to preset it, so that means 1 is Q and 0 is equal to Q bar. And if they're both 1, that means we have normal operation. So here what this means is, once they're both 1, then I start caring about the particular D input. Before that, it's just, these are the only thing that's driving the output. So, just to scroll up a little bit, here I've done a K-map with clear and preset and D and enable as our values, and we have the gray coding here. And if you notice that whenever enable is equal to 0, I just want Q previous, right? And then whenever enable is equal to 1, then I have our two P subcubes, where when E is equal to 1, we have the result C, clear preset not, or D as our value. So when E is equal to 0, we're just going to have our Q previous value. So you guys recognize this? I know I've given you a hint here. Shannon expansion, right? So what you can do is you just have a multiplexer that's driven by the enable signal of the clock. Let me scroll up a little bit for those of you in the back. We have an enable signal driving a multiplexer. The 0 input just has the previous value, right? So instead of having to design even something that's even more complicated, you can use Shannon expansion to reduce the amount of design you have to do. And then we just have clear preset not, which is our design here, or D is on the enable is equal to 1. And then you just have the enable equal to also driving the signal. So does that make sense? Okay, so toggle flip-flops are a unique form of flip-flop that are meant to have the previous value, and then every time it gets in a new value, it toggles. That's the goal. So we want to control when it's not toggling, and we want to control when it is toggling. And when do you think would be a good to use something that just toggles between 0 and 1? let's combine the concept of master-slave and toggle flip-flops. Let me get rid of our Cook machine, finite state machine. And let's go through a pattern here. So I have my initial one is toggling, right? 0 and 1, right? 0, 1, 0, 1, 0, 1. So we have a slave toggle flip-flop. It doesn't toggle until the next one toggles, right? 1, 1, 0, 0, 1, 1. So if we have another slave flip-flop, it doesn't toggle until this one toggles, right? Yep. 0, 0, 0, 0, 1, 1, 1, 1. What does this look like? It's what? That's what? Yeah, you're just counting in binary. It's a binary up counter, right? So that's an example of where you can use toggle flip-flops. So start A, you have 0, 1. If it's toggle is 0, it should just stay in the same state. If toggle is 1, it should move to the other state, where here in state A, Q is equal to 0 and Q bar is equal to 1. In B, Q bar is equal to, Q is equal to 1 and Q bar is equal to 0. And then the toggle is equal to 1. So when clock is 0, it should stay there. When clock is 1 and toggle is equal to 0. And so I've actually kind of gone through here in this truth table. We're building, we start with the SR, we build up to a D, and now we're using D flip-flops with these AND gates to drive a toggle. Q remains the same, and when toggle is equal to 1, I want it to be, if it's 0 and 1, then I want it to be 1 and 0. If it was 1 and 0, I want it to be 0 and 1. And so we have this simulation I've implemented in VHDL. So when toggle is equal to 0, look what happens. I set toggle equal to 1, and you start having these toggling, right? And so it toggles, toggle, toggle. So it's slowing down a little bit, right? So here I've said, notice how the toggle works in such a way that it changes from 0 to 1 or 1 to 0 on every positive edge. That means that toggle flip-flop can be used to reduce input clock speed without affecting the clock of the rest of the circuit. So let's say I want to reduce my clock speed by 8 for some reason. I've noticed the clock is too fast, my timing is off, I'm giving dollars back to the students at University of Mississippi. This is bad. We need to slow down the clock because our embedded system engineer is an idiot, right? So we can set all the toggles equal to 1. Let me scroll up a little bit. Set all the toggles equal to 1. And then just have the clock on the initial, and then Q drives the clock on the next one. Q drives the clock on the next one. And we have our divided signal. And so I've written some VHDL here, reduced clock. Clock and div signal are ins and outputs. And I have a toggle flip-flop component. And I just set toggle equal to 1 here. And then have clock, and I have 2 wires that correspond to these 2 wires, right? And then Q0, Q1, and then div signal. And then, as you notice, when it's 1, it toggles and slows down. When it's 1, it's actually slowing it down by a factor of 8. And it's because we divided by 2 the first time, we divided by 2 the second time, and we divided by 2 the third time. So now this new clock pulse here is just 1/8 the original clock speed. So we'll discuss JK flip-flops, and then I have something I want to talk to you guys about before we dismiss. So JK flip-flops, where I magically heard that Q never, ever, 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 ever equals Q naught. Do you guys remember first lecture? Who invented JK flip-flops? Who? His name's not Charles.
Will and Ben, it starts with a J.
Yep. There, J, and his last name starts with a little. Kilby. Jack Kilby. Very good. Jack Kilby. What else did Jack Kilby do? He did something very important. All of us. What's that? Looking up your first notes. Exactly right. In 1958, he invented the integrated circuit. Everything you do, your phones, your computers, everything is impacted by him. He won a Nobel Prize in 2000 for it. So I've heard people rant about it. No one knows who Jack Kilby is. So at some point later in the semester, I may ask. So know who he is. He's very important. He's impacted every single one of your lives. So here, the objective was to be able to toggle. It must be called a universal flip-flop. So it can be configured as an SR flip-flop, a D flip-flop, and a toggle flip-flop. So based on the inputs, you can do anything. So if you're initially at A, if J is equal to 1 here, and K is equal to X, then it toggles. If it's 0, it'll stay put. And I was hoping that, yeah, the blue screen kind of makes it show up a little better here on the. So here, when clock is equal to 0, it just stays. When clock is equal to 1, there are 0 and 0, it stays again. When clock is 1 and J is 0 and K is equal to 1, you're going to set it to 0. Just like an SR and D flip-flop. When it's in 1 and 0, it's going to set it to 1. When clock is 1 and we have J and K both equal to 1, we want to be toggling. So I've done a K-map here based on this, where when Q is equal to 1, and this is Q next state, Q is going to be 1 when you 0, 0, or 1, 0. And if Q is equal to 1, so that's the points where it stays the same. And if Q is equal to 0, means we want it to toggle and change. And JK is equal to 1, 1, so it's toggling, or 1, 0, as you've indicated, set to 1. So the Q next state is equal to Q naught J or Q K naught. This is actually a very famous and important equation. And so this corresponds to the truth table. So everything in blue here is topical guide objective 4.11. And the finite state machine, when it's 0, 0 and 0, 1, look, it stays. When it's 1, 0, it sets it to 0, 1, and then it's 1, 1, it starts toggling. So we've accomplished everything in the that we expected to do with the JK flip-flop. So as I've mentioned here, and we'll start after JK flip-flops for our next class. So the 4.1 through 4.11 is your homework assignment. So the last thing I want to address, because we still have 7 minutes left in lecture, we're having some discussions in the faculty about creating a course specifically for engineers for coding. One of the things that this is my first time teaching a coding class, and I expect you guys to have a certain level of coding experience. And it's becoming clear to me that a lot of you have not been given this, right? That's not your fault. You guys can only learn what you're taught, right? And so, I want to press pause because I'm going to say some things here. So, yep, do your homework.